So S1 and S2 are subspaces of subset. Okay. Okay. This must be a subspace. These are subspaces of V. No. No, no. I'm saying the question would have said that S1 and S2 are subspaces of V. Which is probably at the end of the notes. Yeah. First chapter. Yep. It'll be after 6 because I've moved it. I don't know if you did a recent pull. You did. Okay. Okay. Go. No. Huh. Oh, I removed it from this. Hey, did you guys check the new course page? That is not in the assignment, but I'm happy to discuss that problem. The assignment is only from problem 6. Yeah, okay. As long as you know that, it's fine. Okay, S1 and S2 are subsets. Does it say subset or subspace? Subspace, right? Not subset. Yeah, that's what I was asking you. Okay, S1 and S2 are subspaces of, I don't know, some V. Okay, if they are subspaces, what does it mean? See, all of this is just blind application of what the definition is. Right, right. So the question is whether S1 intersection S2 is a subspace of V. That's the question. This is given. This is what we want to know. But if this is given, what does it mean? What does it say about S1 and S2? Yeah. Yes, these are subsets of the big set, and they're closed under. Right. Okay. Right. Okay. If you want to verify if this is a subspace of V, what do you have to do? Yes. Common elements. This only has the common elements between them. Okay. Yes. Yes. If it's closed, right? So what is the difficulty in doing that? You don't know how to do it? Is that the question? So here, okay, S1, S2 are subspaces. This we know, right? Now, if you take an element X that belongs to S1 intersection S2, okay, if you, this means X is both in S1 and S2, okay. If I do scalar multiplication of X, we want to know if that belongs to this intersection. If X belongs to S1 and S2, this, okay, let's start like this. X belongs to S1. Does alpha X belong to S1? Hey, S1 is a subspace of V. That means if I take a vector from S1 and I scale it, that will be in S1, sorry. That will be in S1 because it's a subspace. Okay, if X is in S1, that means this has to be there in S1. If X is in S2, this has to be there in S2. Okay, X is both in S1 and S2. That means this also has to be there in both of these because whatever is present in S1 will also, alpha times that will also be present in S1 and S2. Do you see? No. You tell me, how do you do it? So you have to take two vectors. One belongs to S1 intersection S2 and X2 belongs to S2. X1 plus X2. If X1 and X2 belong to S1, does this belong to S1? Yes, because S1 is a subspace, right? If X1 and X2 belong to S2, does this belong to S2? It does. That means this should belong to both S1 and this should belong to the intersection because it's there in both of them. Because X1 and X2 are there in both of them. And S1 and S2 are subspaces. If somebody said these are just subsets, then of course this argument does not work. If this is just a subset of V, if X belongs to S1, alpha times X might or might not belong to S1. Okay? No? If it's not clear, you have to tell me now. Because if you don't ask me now, maybe you'll never ask me. And then this will remain as a question. Yes, why? That's what I'm asking. Okay. When we say X1 belongs to S1 intersection S2, right? That means it's both in S1 and S2. If I say X2 is in this intersection, it's both in S1 and S2. Okay. If X1 and X2 are in S1, does X1 plus X2 belong to S1? You understand the question? What will you need to answer that question? What will you need to know to answer that question? No? Go ahead, yeah. Sure. Here, okay. S1, S2. If you take any element from S, forget about S2. If you take any element from S1, you do scalar multiplication or vector addition, it will be within the circle. If I take any element from S2, I do scalar multiplication and vector addition, it will be in the circle. If I take only these, right, this belongs to S1. If I take element from here, that belongs to S1 and S2. That means the scalar multiplication has to be in here, and the vector addition also has to be in here. Since S1 and S2 are subspaces, yes. If so, if this was just a subset, then this argument does not. You cannot know. It might still see. If these are just subsets, it is still possible that this can be. I'm not sure. I don't know. I have to think about that. If these are subspaces, then for sure this is S1 intersection S2 is a subspace. Okay. Right. Okay. What else? Doesn't matter, right? So if you're talking about linear transformations, let's say from RQ to RP, every point here gets mapped to a point there, right? Yeah, I mean, the definition of a function is like that, right? Function f of x equals y. It simply means f is a function that maps from set of all possible x's to, so it maps from a set x to set y. The mapping is such that every point in x has to have a corresponding element in y, but not all elements of y have to be mapped, right? For example, if I do y equals 0 times x, let's say x is a real number, right? Every x will give me a corresponding y, but this is kind of a trivial function because this function will always return 0. So this is a function that maps from the real line to the real line. All these points, right, get mapped to something here. But in this function, it's a weird function in the sense that this entire line simply gets mapped to 0. So everything from RQ will find a corresponding element in RP. It might not be all of RP. It depends on the nature of the function. In fact, if the matrix A is 0, then all of RP will get mapped to 0. Hey, hold on. There is no what do you mean by linearly dependent combination? linear independence. Okay, you have a linearly dependent set from RQ. Hey, no, hold on. If you're talking about a linear transformation, right? What goes in is a single vector. You don't put in a set. What it takes as, okay, if this box represents the linear transformation, what goes in is an individual vector and what comes out is an individual vector. This does not take in sets. Well, if you're asking, if I have a set of vectors and I want to apply f to those individual elements, that you can do. If I have a set of vectors v1, v2, vm, and you want to apply this linear transformation on each one of them, that you are anyway allowed to do. But here again, you take each individual element, apply the linear transformation, and then you form a new set. That's all. Additivity property of a function. Here, it's simply this. If you have a transformation, not just a linear transformation, all that will take is a vector from RQ and produces another vector from RP. It does not take sets, it does not take anything else. Individual vector goes in, individual vector comes out. Okay. If you say that this function satisfies additivity property, that simply means if I give it x1 and I get y1, and I give it x2 and I get y2, if you say this function satisfies additivity, and I ask you what will you get if you give x1 plus x2, given that you know that x1 produces y1, x2 produces y2, if it satisfies the additivity property, then you don't have to input this x1 plus s2 to this function f to find out what the output will be. You already know what the output is because it satisfies additivity. If it does not satisfy additivity, then you don't know what x1 plus x2 will produce. Scaling is the same. If I know x1 produces y1 and it satisfies the scaling property, I know if I multiply this by alpha, what comes out will be correspondingly multiplied by alpha. Only if it satisfies the scaling property. If it does not satisfy, then I don't know. So for example, say you had a function which simply multiplied, let's say the input was a real number, output was a real number. I don't know what is inside, right? But I know that this function inside it's kx, but let's assume we don't know. If I give x, I get y. This satisfies the scaling property. That means if I give 5 times x, I know I'll get 5 times y, right? Or if x produced y, 5x would have produced 5y. But if this was x square, right? X produced y. 5 times x does not produce 5 times y. It produces, here it is not satisfied. So now if you ask me what will 10 times x produce you, I don't know. You'll have to input and see what you get. But if it satisfies the scaling property, then I know. Okay. What else? That's okay.
I understand the question. Consider this system.
Oh, I see. Okay. The question is, you have a basis bi for Rn, I goes from 1 to n, and then you have the standard basis for Rn again. Okay. Let's say we have a vector x, and the representation of this vector in the standard basis is x1, x2, xn. Okay. What this simply means is that x can be written as x1 times e1. This is the standard basis representation. That's x2 times e2, xn times n. This is a standard basis representation. Okay. Let's say we know the representation of x in the b basis. This is the b basis. Let's say this representation is given by this xb1, b2, xbn. What this means is this vector x is simply, or can be written as b1 times b1 I should really write S here. No, I will leave it. No problem. If this is the representation of the vector x in the b basis, then you can write it like this. And in the standard basis, you write it like this. And then the question is, yeah, can you open it? I think you're supposed to verify if the lengths of the vectors are the same. Yeah. If okay, you're supposed to evaluate. Okay, right. These are the two representations, right? Now the question is, you're supposed to find out what is this. I think this one, and what is simply you're supposed to evaluate this, okay, and then find out what is the relationship between them when I don't know what are the conditions. Both of them is okay. You're supposed to verify the relationship between them when these basis vectors, right, bi, have length 1 and they are perpendicular to each other. Given that now you understand the question. Yes. So you first evaluate these two, and then you're asked what is the relationship between x second norm of x square is the second norm of the representation of x in the b basis square for any general basis b versus an orthonormal basis b. So I want you to work this out, and then what you should find is when this is satisfied, x square will be equal to square. When this is not satisfied, these two will not be equal. Okay. This simply means that if you have an orthonormal basis, then the 2 norm of the vector is simply given by x transpose x. If you have a basis which is not orthonormal, okay, it turns out this is not the correct way to compute the length. See, the length of the vector is its length, right? It's inherent property. But x and xb are its representations in two different bases. Okay, your standard basis is a nice basis because it's an orthonormal basis. If you have an orthonormal basis, then you simply compute the square of the two norm of the vector by simply doing doing the standard inner product. But if you have the representation of the vector not in the standard basis or not in an orthonormal basis, it turns out that you cannot compute the length of the vector anymore simply by doing the standard inner product. So there is a different type of inner product, right? That will give you the length which is equal to this. Okay. We did an example yesterday, right? We had 2, 1. This is the representation in the standard basis. And then we had two other vectors that were bases, right? I'll call them B1 and B2. I think one was 1 minus 1, the other was 1, 2. Was this correct? Right? I think that's 1. Let me call this x. Okay. X is the representation of this vector in the standard basis. What is the length of this vector? Or what is the square of the two norm of the vector? Yeah. No, not root, square. Square of the length. So that's simply what is this? And then what was the representation of this vector in the B basis? We had this, I think this 1, 1, no? Is that right? 1, 1. Okay. Tell me what this is. And then let's say we use the B's representation and we do this. Tell me what you get here and what you get here. This will be 9. Strange. The length of the vector should be the length of the vector, right? It's an internal property of the vector. But when we use the standard basis, the length comes out to be 9, where we're computing the square of the two norm using the standard in the product. But when we switch our representation to some basis B1, B2, well, the basis is like this. This is B2, this is B1. When we switched from the standard basis to the B basis, we found this representation. And when we try to compute the length of the vector by doing the standard inner product, we get a different length. Right? So it turns out that the square of the two norm is given by the standard inner product only if the representation of the vector is in an orthonormal basis. If it's not in an orthonormal basis, this does not work anymore. There is a different, you have to account for the fact that these are not perpendicular to each other and they don't have length 1. It's simply this idea, right? For example, let's say I have a mass, a body, it has some mass m, right? If I use kilograms to represent that mass, let's say it's 1 kilogram, or let's say 0.5 kilogram. Okay? But if I used, let's say milligrams, right? What would be the weight of this in milligrams or grams? Right? This idea of magnitude of a vector, right, is simply in R, it's simply the absolute value. If you simply took the absolute value, right, you'd say, well, this is heavier than this. But that's not correct. You've not accounted for the fact that the references are different. The same thing applies here. The length of the vector is its inherent property. Okay. But the moment you use a numerical representation to quantify that length, different references can give you different results. Okay, especially when you're talking about the length, right? Using the 2 norm, the 2 norm length of a vector as computed by the standard inner product will be equal for a vector for different representations only if the different representations are in an orthonormal basis. If it's not in an orthonormal basis, then you have to correct for the fact perpendicular and they don't have length 1. Just like here, you had to correct if you want to compare the absolute values, right? You have to correct for the fact that the units are different. Otherwise, it does not make sense to compare them. Okay. Okay. What else? See, it's best to discuss everything now. If you're not sure, yeah, just get it clarified. Yes. Sorry. Okay. Doesn't matter. The fact is that it's not equal. That's all. Okay. Let's do one thing. Use another basis C1, C2 just to convince you that orthonormal basis at least seem okay. 1 minus 1. This is 1, 1, but you have a root 2. Okay. Can you find the representation of 2, 1 in this basis C? What is XC? You understand the question? The representation of this vector 2, 1 in the B basis was 1, 1. I want to know what is the representation of this vector X in the C basis, where the two C basis vectors are 1 by root 2, 1, 1, 1 by root 2, 1 minus 1. So I want to know what is XC. How will you find out? Well, you essentially have to solve this problem, right? X equals B. Yeah. And tell me what is the solution. How will you find out? Maybe it's not clear. You have it? Okay. See, when we say we want to find the representation in the C basis, then we are simply asking what are these two scalars such that if I take x c1 times c1, x c1 times c1 plus x c2 times c2 gives me 1 to 1. I know what these are. What are these? This is, there is a 1 by root 2, right? xc1 1 1 plus 1 by root 2 xc2 1 minus 1 equals to 1. I have two unknowns. I have two equations. Let's take the root 2 to the other side. That means we have two equations, right? xc1 plus xc2 equals 2 root 2. xc1 minus xc2 will be root 2. Right? Yeah. Okay. So if we solve for this, 2 times xc1 will be 3 root 2. xc1 will be 3 by root 2. Now that means xc2 will be minus 3 by root 2. Will be 4 minus 3. Correct? Yeah, that's correct. I'm going to keep this to simplify things. Simple. Okay. So the representation of x in the C basis now is this 1 by root 2. Okay. Now tell me what is xc transpose xc. This is your yeah, 5. Now there is no problem. Okay. Why? What is the length of C1? What is the length of C1 and C2? Or the two norm of C1 and C2? Or what is, well, just calculate it, right? What is C1 transpose C1, C2 transpose C2, and what is C1 transpose C2? You guys have it? What is C1 transpose C1? Yes. C2 transpose C1, C2. Sorry? Why is it 1 by 2? C1 transpose C2. C1 transpose is 1, 1. C2 transpose is 1 by root 2, 1 minus 1. You multiply these two out, 1 by 2, 1 minus 1, 0. What does it say about the C basis? The lengths are 1. The two vectors are orthogonal to each other. That means C is an orthonormal basis. And whenever you have a representation of a vector in an orthonormal basis, their two norm lengths will always be equal. Okay, correct. We have time maybe for one more question. No? Yes. What is the question? Yeah. Yeah. Are you sure? That's all? Okay. See, please don't hesitate if something is not clear. This is the time to ask, because once you miss this, there is going to be no other opportunity. Okay. I mean, this semester. If you don't ask now, then you will probably go through the entire course without knowing it, and then you're just trying to get through the course. And don't do that. This is the best opportunity to learn this material. Okay, all right, sure. Okay, see you guys tomorrow.